Okay. My name is Gejun. Oops. You missed this. Okay. My name is Gejun Zhu. I'm from the Maths department.
Today I'm going to talk about the Bayesian analysis in R and one-parameter model. And so if we want to talk about Bayesian analysis. So first we need to talk about the Bayesian rule, Bayes rule. Okay. And here's an interesting problem. Just as suppose your friend told you that he has great nice conversation with somebody on the train, and you need to guess the gender of the person he talked to, but you may guess that 50% that the person is a woman, right? But if he told you that the person has long hair, then you may guess the woman must be more likely, right? So, so if we want to find the exact probability of the what is the probability for that person is a woman, then we're gonna use the Bayes theorem, which is PAI given B is equal to the this is the formula, and the denominator is the total probability function, and this is the actually is prior probability, and this is the likelihood I will introduce later, right? So, but Bayesian analysis in R is different from the using the Bayes theorem. So Bayesian analysis is not just use the Bayes theorem, okay? So the next, just assume you are a skilled programmer, and you just compile the program. You maybe you be confident that the program will run correctly, but sometimes there's some bug in your program, right? So you want to find some data to test the program. First, you find 10 or 100 data sets. Then, yeah, it passed. You become confident, right? And then you find more difficult data to test your program. Maybe you find 1,000. Okay, it will pass again. And then you find more and more and much harder the data set to test the program. Yeah, it passed again. So you become more and more confident, right? The data give you the confidence. Right? So the Bayesian thinking is kind of like the testing the program. You find more data there, then you update your belief about your program, right? So this is the I think is the principle or the Bayesian thinking in our daily life, right? So this is the Bayesian thinking. So for the Bayesian analysis, we use the belief, and so the F theta is the prior distribution which expresses our belief about the parameter before we see any data, but for Fx given theta is the statistical model which reflects our belief about x given theta. Sometimes we call this the likelihood. And the last one is the posterior distribution, and the x1 to xn is the data you got it. And then we after we see this data, we update our belief about the theta, the parameter here, right? So the posterior distribution can express our updated belief after the observing of the data, right? So we use the Bayesian theorem. Here you can see if it is a continuous distribution, we use the integral, and then this the same as the previously. So if we have independent identical distribution, the data there, usually we use ID observations xa1 to xn, then we get the likelihood, because this is sometimes we call it likelihood, right? So we use the the multiplication of all the theta given xi. We use the ln theta. Summarizing to that one, because this one, after the integral, it must be a number, right? So it doesn't depend on this theta. So we can just use a proportion to the numerator here, right? So this is the basic ideas about the Bayesian analysis, and I'm going to introduce two models, one parametric models. The first one is binomial model, and the next one is the Poisson model. The binomial model is the prior distribution is a uniform distribution. This is the specific example, which the prior distribution is a beta distribution. It's a uniform, and uniform distribution is a particular beta distribution, which is A is equal to 1 and B is equal to 1. And the likelihood function, we can see we use the previous here. We find the multiplication of all the fxi given theta. So we find the it's proportional to theta to the power of x and times 1 minus theta to the power of m minus x, and then we use the prior distribution times the likelihood function, then we get the posterior distribution, right? So the x given theta, after this theta, the distribution of the theta is to the beta x plus 1 and x minus x plus 1. And this is the beta distribution also. So if the prior distribution and the posterior distribution are the same distribution, so we can call this is the conjecture prior. Okay, and I will give you example. Then I will show this example in the R. So how to do that? This example is each male, female of age 65 or over in the 98 general social survey was asked to whether they were generally happy, and y is equal to 1 if the respondent I reported being generally happy, 0 otherwise. Okay? This is the binomial distribution. They only have two possible outcomes, and the data is the 129 individuals surveyed and 118 reported generally happy, and 11 did not report generally happy. So we can use, we can see the model looks like this. This is beta, A is equal to 1 and B is equal to 1. And this is the uniform distribution. Likelihood, we plug in the data because the success we're interested in is 118 and 1 minus theta, which is not happy, is 11 people. And so the posterior distribution, we can see we use the probability times likelihood, and we get the beta distribution, which is 119, and the next, the other one is, yes, 12. Okay. So we get use the R. See, the graph looks like this. The dashed line is the prior distribution, because this is a prior probability, because this is uniform, so it looks like that X line here. And the posterior, which as we can see, is this, is beta 118 and 12. 119 is 12, I'm sorry. I'm going to show this in the R. If the prior probability is it's not a uniform distribution, it is a beta distribution, we can get this actually the similar results from the Bayesian analysis. So the prior is a beta distribution. This is the beta distribution, and if this is the likelihood, and this is the posterior distribution, you can see that is the posterior distribution is actually in the middle of the prior distribution and likelihood distribution. Sometimes we call this like I forgot this word. Compromise between the prior and the likelihood. Okay. And the next model is Poisson model, and we also have the prior distribution, but this time the prior distribution is a gamma distribution. Gamma distribution we can write in this way. This is gamma function, and the theta to the power of n minus 1 and to e to the power of negative b times theta, and the likelihood function is we find the multiplication of the single Poisson distribution. So we get, because this part doesn't depend on the lambda here, so it only depends on the data here. So we just write the function c of x1 to xn, and it times the other part here, right? So then the posterior distribution is still gamma distribution, because they have the same structure to the other part, so we can write this posterior distribution as the theta to the power of a plus sigma xi minus 1 to then times e to the negative b plus n then times theta. So this is the posterior distribution of the gamma distribution of this, which is a Poisson model. And this is example for the Poisson model, and we have 155 women, and their age over 40. We're going to compare the birth rate between those who have a college degree and those who don't have a college degree. So for those who have a degree, we use y11 to the yn1 then 1. Okay, that means we have n1 women, they have the college degree. And for those without the degree, we use y11 to the yn2 then 1. That means there are n2 women, they don't have the degree. So they all follow the Poisson distribution, and the first one, the parameter is theta 1, and the second one is parameter is the theta 2. And then so we can change the data to this form. So those who don't have the bachelor degree, n is equal to 1, and totally they have 111, and oh, I'm sorry. Totally they have the 211% and n1 is equal to 1. They what's that? Totally they have 217, and then 111 people have they have the less bachelor degree, and the second group they totally 66 people and 44 people have the bachelor degree or higher. So we'll compare these two groups, then we plug in all the numbers to the model. Then we just assume that theta 1 and theta 2 they have the same gamma distribution. The parameters a is equal to 2 and b is equal to 1, right? And then we got the posterior distribution as theta 1 is given the data, we see the gamma distribution is 219 and b is equal to 112. And theta 2, then given the data here, we got the gamma distribution with parameters a is equal to 68 and b is equal to 45, right? So this is the graph of the gamma distribution in R. So this is the distribution of theta 1, and this is the distribution of theta 2, and this is prior distribution. So from this, we can see the prior distribution of theta 1 and theta 2 are the same, but after we saw the data, we update our belief that theta 1 follows this one and theta 2 follows this one. So the data will help us to update our belief about the parameter, right? So I'm going to show you the program in R. Okay. So let's see. I used R Markdown to do this this file. So we see here. So the first example we see this is the normal distribution. So we just set two parameters, A is equal to 1 and B is equal to 1. And then this is the what's this? So we're gonna see the people who say they reported they're happy, and and this is the not happy. How many people they didn't report they're happy. So we use the H is equal to, because the number for here we can see 18 reported general happy and 11 didn't report general happy, so H is equal to 19 and not happy is equal to 18, right? So we're going to use the curve function, and this is the beta function. If the beta function, you can see if there is a D here, that means the beta distribution. And if it's Q here, that means quantile beta distribution. And if they use R here, that means you're going to generate the random beta distribution. That you're going to generate some like the sample data there, right? So the curve you see here. So this is the curve for the posterior distribution here, and then because we use A plus H and B plus NH, so you can see this is a posterior distribution, and then this is the prior distribution, which is the uniform distribution. So this is only a line here, and with the this here is equal to 1. So we add some legend to this graph. So that means the dashed line is the uniform distribution, and this is the posterior distribution, the graph of the posterior distribution, right? So this is the posterior distribution with the uniform prior, and then we're going to see which is a beta prior. So this time we'll set A is equal to some other number, which is not equal to 1. A is equal to 3.26, B is equal to 7.90. We're going to see how does this graph look like. Let's see here, if right? So this is the posterior distribution. See, we use A plus S and B plus H here. And then because the beta distribution we for the first one, which is only the uniform distribution, so we don't need to just add 1 here. But for this one, this is beta, so we used S plus 1, because when we use the formula, we can see that one is theta plus 1. So we need to add a 1 here. This one, and the next this is prior distribution. Okay. We see the legend. So this is prior, and this is likelihood, and this is the posterior distribution. Okay, the same as that one. The last one is the Poisson distribution, which is A is equal to 2. We assume that the prior distribution with parameters A is equal to 2, B is equal to 1. So we said A is equal to 2, B is equal to 1. And then this is the first group. They have totally they have 17 people, and 11 they have the with the degree. And for here, this is the second group, 66 people, and 44 they have the high degree, right? Yeah, bachelor's degree. So the curve we see, yeah. Oops. Is that where? Oh. Oops. Let's see. Is equal to. Oh. Did I wrong here? No. Yeah, this part. Oops. Doesn't work. Oops. All right. So I want to use that one. Okay, so this is the gamma distribution. We use the D means that the gamma distribution. So this is the posterior distribution, and then for here this is prior. See here. All right. So this is prior distribution, and then this is the second group, and we can see the posterior distribution. And for the legend one, for the legend here, I spend a lot of time because there are some math expressions here. So this is the this is for theta 1. We're gonna see the posterior. Oops, doesn't work. So first, previously we see the theta 1. We have the prior distribution with A is equal to 2, B is equal to 1. But after we've seen the data, we see it becomes 1.95 and 5357, right? Okay. So and this is the mean of the should be here. So this is mean of the first group, and this is the quantile. It's quantile gamma distribution. We use Q gamma. Then this is the interval, confidence interval, which from 0.025 to 0.975, right? This is oops. So it's between 1.70 and 2.2 here. So this is 95 confidence interval. And for theta 2, we're going to do the same thing here. So for the posterior mean of the theta 2, we got 1.5. And then the mode is 1.48. And then the quantile 95 confidence interval, we got 1.17 to the 1.89. Okay. And then if we use the prediction for these two groups, we use some data to test it. This is theta 1 predict. We use you can see the dn binomial. So this is the binomial distribution with how to say this one? or is the nominal binomial or negative binomial? It's the negative binomial distribution. So because yeah, density of the negative binomial. I forgot to introduce the here because so after this no, it's here. After this is the negative binomial distribution. Oops, it doesn't work. Okay. So negative binomial distribution, this is y and this is size. We size equal to, we plug in all the numbers right here. So y, we just said 0 to 10. And then we see from this is the, oops, I didn't run this, sorry. And right. So this is the prediction for theta 2, and then we're going to plot this 2 to see. All right, let me just run this together. Oh. So you can see this is the prediction for the y n plus 1, because we know the y1 to the yn, but we need to predict the yn plus 1. So this is the graph we're going to take a look. And it's not very clear for the color here. This is one, it's black one, which is less than the bachelor degree. And this is the bachelor degree. So you can see for here, they have the bachelor degree, the person have the bachelor degree have the larger probability than the less than those who didn't have the bachelor degree, right? So this is a prediction for the probability of the y plus 1. So I think this is only part of the Bayesian analysis, and I don't know whether I explain them clearly. So if you have any questions or problems, just let me know. Okay, so that's it. Thank you.
Okay. All right.